Our next example is a rational function, and we'll start off with the domain. Again, we can factor the denominator because it's the difference of squares to help us find the domain. See, the domain is all real numbers excluding -1 and +1. And since we don't have any of these terms repeated in the numerator and the denominator, there's nothing to simplify, so this is in lowest terms. And what that means is we have vertical asymptotes at x equals -1 and x equals +1. Since the domain, since the fraction is 0 and the denominator at plus or minus 1, so we have our domain. Next, we can take a look at any zeros, and we see that we have a 0 by setting the numerator equal to 0. If 2x squared equals 0, that means x equals 0. If you recall from algebra, that has multiplicity 2, so we know the curve touches the x-axis at that point. Suppose we could also mention that these have multiplicity 1, since the exponents on those two terms have power 1. That just means that if we look at the sketch of the curve is going to be across the vertical asymptote, which we'll see from all the other parts of our equation once we get there. Next, we have symmetry. And if we look at this equation by replacing a negative x everywhere we see x, that is f of -x, then we will see that this is an even function, since all of my x terms are squared. I am left with the original function, and an even function has y symmetry. So really we only have to worry about half of this graph from 0 to infinity. But I'll probably forget and go from -infinity to infinity anyway. Okay, so we have vertical asymptotes, zeros, symmetry. Next we can look at the first derivative. We've got two options. We can take a look at the first one or the second one. And with the first one, we have a quotient rule. With the second one, we have a quotient rule where the derivative of the bottom is a product rule. That sounds like more work to me, so I'm just going to take the derivative using that first option. So we have derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. At this point, we want to see if we can factor anything out, if we can simplify this at all. And I notice a 2x in both of those terms, so let's factor out a 2x, and we're left with 2 times x squared minus 1 minus 2x squared. Suppose we also have a second 2 that we can factor out of the top. We'll do that on the next step. So we have 4x, x squared minus 1 minus x squared over x squared minus 1 squared. Combining like terms, we have a positive and a negative x squared. And we are left with 4x times a negative 1 is negative 4x divided by x squared minus 1 squared. All right, all that to get our critical values. If the top equals 0, that means x was equal to 0. For the bottom equals 0, that is when the derivative is undefined, we have x equals plus or minus 1, since this factors like so. The plus or minus 1 shouldn't be too surprising since there are vertical asymptotes at plus or minus 1, and we have to watch out for those. Here's our number line for our first derivative with our slopes, and I've got negative 1, 0, and positive 1. Technically, plus and minus 1 are not critical values since they weren't part of the domain of the original function. They still go on our first derivative number line, and if we can remind ourselves, we knew that these were vertical asymptotes. You could just put a dotted line there to remind yourself that those are vertical asymptotes. All right, so we need a test value to the left of negative 1. How about negative 2? And we're going to evaluate our derivative at negative 2. So I've got negative 4 times a negative 2. And then on the bottom, no matter what we take x to be for the bottom is always going to be squared. So we're always going to end up with positive on the bottom. So we've got a negative times a negative divided by a positive, and that gives us a positive. Next, let's pick negative 1/2. We have a negative 4 times a negative divided by, again, divided by a positive. So this is increasing again. Then we'll take a positive 1/2, and we have a negative 4 times a positive divided by a positive is a negative number, so decreasing. And then we'll take one more. A negative 4 times a positive divided by a positive gives us a negative. So what features do we have here? Well, looks like we have a local min, not max, I can write, a local max at 0. Notice also that we have asymptotes at negative 1 and positive 1, so even if the derivative sign had changed, we would not have a max or min there. So that is our first derivative information. Now we can take a look at all of our first derivative steps and see which would be most convenient to work with for our second derivative. And to me, most convenient for the second derivative looks like it would be that step right there. So we'll use that for our second derivative. F double prime of x, again we've got quotient rule, derivative of the top times the bottom, minus the derivative of the bottom, here we have a chain rule, times the top, all over the bottom squared. And here, this is it to the 4th power now. So we'd like to see what we can factor and simplify from here. And I see a negative 4 and a negative 4. I see an x squared minus 1 and an x squared minus 1. And that power is going to be to the smallest power, which would be to the first. That looks like all we're going to have to factor. So I've got a negative 4 times an x squared minus 1 to the first. Then what's left? An x squared minus 1 minus a 2 times a 2x times an x is a 4x squared, all over x squared minus 1 to the fourth. Well, it looks like we can simplify one of these with one of these. And it also looks like we can combine like terms up here, which leaves us with negative 4 out front, negative 1 minus 3x squared over x squared minus 1 cubed, which, if we factor out a negative 1 and rearrange this so it's in descending order, we end up with 4 times 3x squared plus 1 over x squared minus 1 cubed. Alright, that's not too bad for a second derivative. And we are interested in looking for the possible points of inflection. Possible points of inflection will happen when the numerator is 0 or when the denominator is 0. If we look at the numerator, we'll notice that x squared gives you a positive number, multiplying by 3 gives you a positive number, adding 1 gives you a positive number, and multiplying by 4 also gives you a positive number. So the numerator will not give us anything new. We can set the denominator equal to 0, and we end up with plus or minus 1, which again should not be a surprise since that's where the function was undefined to begin with. Doing our number line, taking some test points to the left here. Again, we noted that the top was always positive. For the bottom, if I take negative 2 squared, I get 4. 4 minus 1 is 3. 3 cubed is a positive number, which gives us concave up. Let's take 0 as our next test point. Top is positive. 0 squared is 0, minus 1 is negative 1. Negative 1 cubed is negative, so concave down. And then a 2 will give us the same kind of thing as we saw before. Positive over positive, concave up. At this point, you might be tempted to call this a point of inflection, but it's not, since the function is not actually defined at x equals negative 1 or positive 1. That's why we put our dotted line here to remind us that we have some asymptotes there and not features like maxes, mins, or points of inflection. Alright, so we're going to try to put all this together. There's all of our features all at once. Kind of hard to see. Really, I just care mostly about the number lines. And we know we've got asymptotes at positive 1 and negative 1. We saw that we had a 0 at 0. There's one last thing that we forgot to mention, which we should do now, and that's the end behavior. So the end behavior is what happens as x approaches infinity. So if you remember, our function was 2x squared over x squared minus 1. And we can find the end behavior of this by multiplying the numerator and the denominator by x squared, or we can use L'Hopital's rule since it's an infinity over infinity type of problem. Since we just learned L'Hopital's rule, we might as well do that one. So this gives us the limit of 4x over 2x, which we can algebraically simplify to just 2. So the end behavior is 2. What does that mean? That means we have a horizontal asymptote at y equals 2. So here's y equals 2. As a reminder, the curve can cross a horizontal asymptote, but not a vertical asymptote. So looking at our number lines, we have something that goes like this, something that goes like this, something that goes like this. Notice all the features. We have a function that is increasing and concave up from negative infinity to negative 1, increasing concave up, negative infinity to negative 1. Then we have a vertical asymptote, and it flips across the vertical asymptote. We got that from the multiplicity of the vertical asymptote. Then it's increasing concave down with a maximum at 0. We had already seen that we had a 0 with multiplicity 2 at x equals 0. That gives us our max. Then it's decreasing but concave down. Take note of the symmetry here as well, and same with the other side.